welcome again. It's very great to have you all here. This is the first day of our second week of the Learning Week series. And today we are going to have our energy harvesting sessions with Nowi. So I'm very glad to have our speakers today, and I would like to do a very brief introduction for you to Nowi and our speakers of today, but of course they will introduce themselves way better in their part. But Nowi is a semiconductor company that is specialized in energy harvesting, power management, integrated circuits. And today our speakers from Nowi will tell us all about energy harvesting technologies and how they are accomplishing it today in Nowi. So today we have Ines from Nowi. She is the sales operations lead, and also Gerrit from Nowi. He is the application engineering manager and senior validation engineer in Nowi.
Hello, everybody. I am Ines Gärtner, sales operation lead at Nowi. I'm German. I have been living in Brazil for many years, and now I'm in the Netherlands. I have a degree in business administration and have worked in the semiconductor industry for over 3 years, and in IoT as well. And I love audiobooks and cats. And this is Gerrit.
Yes, hello. My name is Gerrit, Wagt, application engineering manager and senior validation engineer at Nowi. I'm in the semiconductor industry for over 20 years, working for bigger companies like Texas Instruments, NXP, National Semiconductor, mainly in the role of validation engineer, application engineer, working on RF products, but also amplifiers and precision products. So a wide variety of semiconductor companies.
Great, so welcome to our webinar about energy harvesting technologies. We will have a quick overview about Nowi, about what energy harvesting is, and about Nowi solutions, and then we will dive into implementing energy harvesting and have a closer look at the autonomous NB-IoT development solution. So Nowi is a fabless semiconductor company founded in 2015. We make energy harvesting power management ICs. Our headquarters are in Delft in the Netherlands, and we have sales offices in San Francisco and Shanghai. And we work with many partners of the IoT ecosystem, such as module makers, connectivity providers, design houses, and IoT solution integrators. Our mission is to connect the physical and the digital world by solving the power bottleneck of the low power IoT devices. So what energy harvesting basically is removing the user of the loop. Usually you would bring energy to the devices by batteries and wires, but we actually can use a lot of energy that is around the device. So this brings a lot of benefits because you can enable new applications, new features. You can bring down the cost of ownership, and you can make the IoT solution more sustainable. By the way, did you know that we dispose of 15 billion primary batteries per year? And with this, we pollute an area of around 300,000 square kilometers, which is about the size of my home country, Germany. So let us see how we can reduce these primary batteries and check how the energy harvesting process works.
Yes, indeed. So the energy harvesting is all about obtaining energy from around you, from around the application, basically. And with this energy harvesting process, we can see how those things work, and we will go through the different steps. So first you have an energy source. So I mean that there should be some energy where you can extract energy from. Subsequently, there's a harvester that converts the energy, the ambient energy, into the electrical domain. And in order to be able to store it, you need to usually convert the energy, and that's done with a PMIC, a converting chip that Nowi is designing and developing. Energy is stored in the storage element, and subsequently it can be used by the application. So if you talk about the energy sources, there could be several energy sources around an application. It could be light, it could be something like movement, there could be a temperature gradient, temperature difference, or it could be a radio signal, for instance. There could be more. And each time for an application, it's the trick to select the right energy source to be harvested, right? And we have to assess, how much energy is there, and would it be possible to get that energy? So, for instance, light, right? If you have a bright sunny day outside, there's a lot of light, so then light would be an attractive way to harvest energy. While it could be like on a motor or something, or an engine which really heavily vibrates, then vibration could be a really good option. Temperature, there could be temperature differences, right, with a hot pipe or something where you could extract energy from. The radio signals are all around us, so they're basically there. The question is always how much energy is in there. So so several possibilities to harvest energy from. When the energy source is determined, it becomes on how to harvest it. So you need a harvester to convert the energy. For solar, for light, it's the solar cell, also called a PV cell, photovoltaic cell. The more light on the PV cell, the more energy that can be harvested. And for vibration, could be a piezo element that kind of resonates, vibrates. For temperature gradient, there's the TEG, thermoelectric generator. So it works with a temperature difference on the two plates. So you have the bottom plate and the top plate, and the temperature difference between the top and bottom plate will represent a certain power that you can harvest. RF will be harvested with antennas. So these four different harvesters, they are a bit different from each other in the sense that solar and TG is a DC signal. The piezo is a kind of AC signal. Same with RF. And the way these things are converted depends a bit, because also like RF antennas are selective, so they can only harvest typically at a particular frequency, or at least small bandwidth. So that is something to take into account when selecting the harvester, and also in combination with the RF source that is expected. So they should match each other, basically. So then the conversion of the energy signal. So once the harvester has collected the energy, typically we need to boost up the voltage in order to store it in a storage element. We want to do that in an efficient manner, because it takes a lot of effort to harvest the little energy that is around us. So you don't want to spoil the energy. So the whole system, the whole energy harvesting system, you want to work it, let it operate as efficiently as possible. So that is also what a PMIC does, a harvesting PMIC, harvest in an efficient manner, but also it needs to adapt to a changing environment. This is called MPPT, and it's basically, you can imagine if the light environment changes, like we see in this short animations. For instance, you have a PV cell on your watch and you're walking outside, so your sleeve might go over the watch, then your light condition changes instantly. So in the PMIC, power management IC need to adapt to that quickly in order to stay efficient, operate in an efficient mode. So this mechanism is called MPPT, maximum power point tracking. So it really tries to track it wants to bias the solar cell in a way that it's always operating optimally. This can also be seen in this this small graph. So on the horizontal axis is voltage. It's kind of the load or the biasing, how you bias a PV cell, it depends then how much energy you can extract from it. So at the maximum power point where you can extract most of the power, for instance, in this 800 lux case, like 2.2 volt, it's where the maximum power is. If you would operate it at 1 volt, for instance, you only have half the power. So with the same light condition, with the same environment, but just how you operate it is determining how much power you can really extract from the PV cell. So it's really important to always find the maximum power point in order to harvest efficiently, because you can spoil quite a huge amount of energy. The storage element. Storage element could be different types. What's very common is lithium-ion cell. They're in different technologies. But what's common for lithium-ion is that it has a constant voltage over a large state of charge. So that means that the voltage remains stable. If the battery is, or the storage element is 20% full or 80% full, the voltage is roughly the same, and it has very little self-discharge. So it's a very good example of a rechargeable system, rechargeable storage element. What does become more popular now is also supercapacitors. It is a capacitor in the traditional way. Also means that the voltage is proportional to the state of charge. It means that the more full the battery, the supercap gets, the higher the voltage. So this is something to take into consideration for your application. Can your application handle that? Advantage is that you can charge it from 0 volt on. So while lithium ions, you always keep a certain at a certain voltage level. It's not recommended to fully discharge it. So that's why supercapacitor also is very suitable for battery-less applications. So you can really charge from 0 volt on. It has a relative high self-discharge though, so that's a difference with the lithium-ion. And then nowadays there's also hybrid supercapacitors, which are kind of in between lithium-ion and supercapacitors. So they have modest self-discharge. The voltage is sort of mainly proportional to the state of charge. So it is not as flat as lithium-ion, but and it's kind of halfway, I would say, between lithium-ion and supercapacitors. So then there's the application itself. So all this energy harvesting is meant to be for the application. So this is the consumer of all the stored harvested energy. Basically, also the application sets the requirements for the energy harvesting system. So how much energy is needed? Do I have high peak currents? What is my consumption profile? Should the application work autonomously? So that has implications for how much energy I have to harvest. Is it for indoor? Is it for outdoor? So there's a lot of things that start rolling from the application. So if we are going to look at an example of how would a harvesting system look like. So this is an example where we show solar harvesting. So you have the sunlight or indoor light. You have the PV cell that absorbs the sunlight, converts it to electrical domain, and then the energy harvesting PMIC boosts up the signal such that it can be stored into the storage element and then used by the application. In this case, it's a remote control. So that's an example of solar harvesting. So now let's take a look at the Nowi solutions, what we offer. Ines, can you tell us more?
Sure. So Nowi provides the components for the conversion step, as Gerrit explained us now. Traditionally, you would have energy harvesting ICs that use inductors and several other components, capacitors, resistors, between up to 15 or even 20 additional components. And thus you would sum more cost of BOM, of bill of materials. You would need more board real estate, and it's also more work to integrate all these components. So Nowi's chip CODIUM is a capacitive energy harvesting IC. It doesn't need inductors, just a couple of capacitors, so we can call it low bohm converter. Nowi's chip DIATOM, which we have launched in March this year, besides being a capacitive energy harvesting IC, it also has power management features. So this brings down the total implementation cost even further, because you can replace some of the components for the power management and for the ecosystem. So let us have a closer look. CODIUM, our low bohm converter, is really small, QFN 16 package of 3 by 3 millimeters, and you would add roughly 2 cents of assembly bohm. On the energy harvesting side, it has a really good performance of about 80% of efficiency. The maximum power point tracker adapts within 1 second, which is really fast. And it is optimized for indoor and outdoor light in a power range of roughly 10 microwatts to 2 milliwatts. We are very proud of this one because we won the Innovation Awards in the category of embedded technology for the CES in Las Vegas this year. This is really good. And DIATOM, our new solution, is also really small, QFN 28 of 4 by 4 millimeters. It adds assembly bohm of about 7 cents. And on the energy harvesting side, the performance is even better, over 90%. The MPPT adjusts in only half a second. And besides indoor and outdoor light, you can also use piezo, TEG, or RF. So this gives you a wide range of solutions which you can use in your project. The power range goes from 15 microwatts to 50 milliwatts, and it has a cold start feature. So your IoT solution can actually be batteryless. And there are the new power management features, LDO, USB charging, and battery protection. So in short, these are small, cost efficient, simple, and high performing. So this is really nice. Let's have a look on implementing energy harvesting. So low power devices can be used in many categories and verticals of IoT, such as industrial sensoring, asset tracking, smart metering, smart home, and so on and so on. And in many of these applications, it comes down to some points which are the challenge for mass deployment and big IoT projects. The sensors and devices need to be as small as possible and as cheap as possible. Also, you want the devices with a lot of features and actions that they would provide. So this all consumes power. But on the other hand, you want the battery, the device, to last for years or even never swap out battery. So here, where energy harvesting can help to win this challenge, there are many great examples. Here are some of them. For example, sensors, which you could apply in smart homes or smart buildings. The sensor measures temperature, humidity, CO2, and so on. This data is collected and transmitted by cellular IoT, and it goes to the data platform of the user. This could be a consumer app or the platform of the utility or of the facility manager. And then they can analyze the data and act on it. Another great example would be a soil sensor. Here, the sensor measures the electrical charge of the soil. The more water is in the soil, the more charge can be stored. And this data is again sent to the platform. You would deploy the device in vast areas or remote areas. So the farmer can tell by this data if they need to act, put more irrigation, or if the soil is in proper conditions. So this is a great example. And another one would be this radiator valve. So this one is powered by TG using the temperature gradient between the heating body and the ambient temperature. And you would collect the temperature data, send it to the application, and get back a command to open or close the hot water flow so you can regulate the temperature. And on the right side, you can see the autonomous Thingy 91 plugin board, which many of you know or even have. And this is a really nice platform to get started to develop IoT projects with LTE-M, NB-IoT, and GPS. So we have many examples. I'm sure you have also very good ideas to put into practice. So how can we design in energy harvesting? Can you tell us more about it?
Yeah, sure, Ines. So if we talk about a typical application, what we see happening a lot is we're talking about mainly about IoT devices, which normally have primary batteries. So there's no wires on there. So usually those IoT devices, they measure something, right? So they send something, and maybe they steer something, they activate something, and then they send the result by a communication standard. So this is a block diagram of how an IoT device would look like. On the left-hand side, you see the harvester. Again, this is the PV cell. Then the energy is converted with the PMIC, stored in the storage element. And then from the storage element, it is available for the actual application. So the MCU runs on the storage element, but also the actuator, the sensor. And then things can be sent over narrowband IoT or BLE, something like that. So that is what a typical application looks like. So how do we design this? Typically, when we design an energy harvesting system, we start with the application, because the application sets the requirements for everything. So we basically start at the back end. So we look at operating voltage. So on which voltage should the application run? How much power does it consume? Are there any other features that are needed, that are desired? Right? Do we need an LDO, or can it just be one single voltage? So then you can use the battery voltage. Subsequently, you're going to look at the harvesting environment. So what kind of harvesting source is there? So would it be solar? Would it be temperature? Would it be RF? So basically you select the source, and also the PMIC, so the power management unit, can be selected based on what the application needs in terms of features. Do we want to support also USB charging? Do you want to have the over voltage protection, under voltage protection of a battery? So and the harvest specifications themselves, of course. So the DIATOM has quite a bit of a wider input range, so it accommodates for more harvesting types than CODIUM. CODIUM is our kind of small, simple, and easy to use step-in model, and then DIATOM is the more feature-rich version of it with a lot more functionality. So the harvester should be selected. So it's a PV cell. Is it indoor? Is it outdoor? Where will the application be used? So that determines a lot about the harvester that you select. And eventually, once you've selected all your components, you did all the configuration, then you're gonna look back on what did I realize, right? So how much energy does it consume? How much am I going to harvest? And yeah, is this application going to be energy autonomous, or yeah, is it battery extension, what we call it, right? So you can extend the lifetime of the battery, but then eventually you have to recharge in another way, for instance, by USB. So typically, how an IoT device works, since it's typically transmitting, during the transmission, you do use quite a bit of energy, more than you harvest, but then for a longer amount of time, it's kind of silent, right, in idle mode. So that gives you the opportunity to harvest a lot of energy, store it in the storage element. And hopefully you can get to a balance there where you harvest equal amount of energy than you consume. And that means that you will be energy autonomous. So since these energy peaks are typically there, you need to take things into account for your storage element. You need enough capacity. You basically need enough reservoir. And yeah, obviously, besides that, it's also the operating voltage needs to be good. Maximum current that you're going to draw in this energy bursts, because that determines the battery selection, basically. Some batteries can be better charged or discharged with higher currents than others. So that comes with selection of the battery. So those are some aspects that are important. What I maybe missed during the MPPT explanation is that Nowi has quite a different approach in terms of MPPT algorithm than a lot of our competitors, because we really measure the maximum power point, while our competitors are measuring, do a kind of estimation. They have a ratio, so they don't get as close to the maximum power point as we do. So that is really helpful. And yeah, the inductors, right? So we don't use inductors, so that's really also our key driver that enables for a good integration. So we yeah, the AMDS. So one of the prototypes that we made, or the collaboration that we did together with, that's your slide, right?
That's my
You want to take over?
Yeah, sure, no problem. So we would like to show you a great solution to get started quickly with energy harvesting. It's the autonomous NB-IoT development solution. And it's completely energy autonomous, which is nice. It uses NB-IoT 2. And it is a joint solution with Murata, Deutsche Telekom, and Nowi. And we are very proud because it won the finalist award at the IoT Solution World Congress. And I would like you, Gerrit, to walk us through the components.
Yeah. Yeah, so what we developed is a small module, a small PCB basically of 1.4 by 2 centimeters. This contains several items. So it's narrowband IoT. So there's a wireless communication module from Murata, which is under the shielded box. This module also accommodates for the small new SIM from Deutsche Telekom. So the SIM card is integrated into this chip, so that saves an awful lot of space and makes it also really small and tiny. Right, the SIM card on itself would be close to the board space already, and that together with our Nowi chip, which is on the right front here. It's really tiny, only requires a couple of capacitors and doesn't have any inductors. So the inductors usually are as big as, or maybe bigger as, the Nowi chip itself. So not having inductors really enables for real small form factor solutions. So what we did is we used ambient light here together with a PV cell that connects to this board and to the Nowi harvester CODIUM, the CODIUM chip. And then the energy will be stored into a rechargeable battery, and that supplies this whole module. So that's basically something that we realized, and we've been testing this to demonstrate what the outcome is. So what we tested we used this module in combination with a Panasonic PV cell for outdoor usage under a cloudy environment. That means that we accommodated for 3000 lux. So 3000 lux represents an outdoor cloudy environment. And the module harvests energy for 6 hours. So given this ambient energy source, we were able to charge with a current of 1.1 milliamp, which represents that you can harvest 12 milliwatt hours per day. And on the bottom right, there's some numbers what we measured in terms of consumption. So all these events that you see there, they add up to 2.19 milliwatt hours for one narrowband IoT transmission. So if you divide those two numbers, that means that you can support up to 60 narrowband IoT transmissions per day when you want to be really energy autonomous. So yeah, I think this is a nice example of how small and how tiny such an application can be. And yeah, this enables for integration in small form factor IoT solutions, I would say.
Amazing. You have learned a lot about energy harvesting technologies today, and it's not so difficult to integrate energy harvesting, right? And there's a lot of benefits that can come from this technology. So you can get started with energy harvesting. You can register for the new version of the ANDS, which should be available by November. Also stay tuned for the Nowi documentation on the IoTCreators platform and in the library. And if you have other questions, want to start your own solution, you also can reach out to Nowi on our website. We would like to say thank you for listening, for watching. Thank you, IoTCreators, for the opportunity to talk about energy harvesting. And back to you, Jensit.
Thank you very much to both of you for your presentation. I think it was super informative. And we do have a couple of questions, so maybe I will directly start with them. I will read them out to you. And the first question is actually, Gerrit, you started to mention that in your mentioned that topic, but I would like to remind this question again. So Ruben is interested in understanding a little bit more about how Nowi is differentiated from others in the space. So what is the, let's say, unique selling point of Nowi compared to the other competitors?
Yeah. So what Nowi clearly does different is not using inductors. So we have a purely capacitive converter, and the advantage is that it enables for easier integration. So we see also examples where we are part of the communication module. So we completely integrate with the communication model, and that would not be that easy when you would use inductors. So inductors are usually bulky and not easy to work with, right? And they're more expensive than capacitors. So that is one of the examples that we clearly differentiate on. The other one that I touched already briefly was MPPT. So we really have we really measure the power that we obtain. So MPPT is an algorithm, right, that manipulates several parameters to make the optimal harvesting of the whole system. So we probe all these different configurations and we really measure the performance, and then we get to the optimal power that we harvest. So the traditional way of getting to a sort of a maximum power point tracking is with a so-called open circuit measurement. So then you measure a voltage and then you take a certain ratio of that, and that ratio that you consider as the maximum power point. So you get a sort of an approximation. So yeah, that is in short what we do different from competitors, other than maybe adding features. We have several added features, especially in the DIATOM, such that as little external components are needed as possible. Right, so a lot of application would still have the opportunity to charge through USB, or some protection facilities for the battery. So those kind of things we do have integrated in our DIATOM chip.
Yeah. Okay, thank you, Gerrit. And also, to my knowledge, Nowi has one of the smallest the energy harvester chips. I believe this is also a differentiator, right?
For sure, yeah, for sure. The size is most of the things are integrated. You only need, depending on the product, a couple of capacitors, and the rest is all internally. So what we see as a differentiator is that a lot of our competitors need quite a bit of circuitry around their chip. Like it could be configuration, like resistors to set a certain reference level or a certain bias level, or to set the LDO level or anything. So yeah, this is really meant to be lean and simple, easy to adopt, and easy to integrate. So that's the aim.
Perfect. Thank you so much. And there's a question from myself. I will briefly, I tried to answer it from the chat, but I guess I couldn't manage that. So the recordings will be shared with everyone by the end of this week. I really hope. It's a bit hard to manage, to edit the recordings while managing the webinars, but I will really hope to send every recording since the beginning of last week by the end of this week. Thank you for your patience. Okay, moving on with the next question to you. So does your energy harvesting solutions only use light as the energy source, or do they use heat, kinematics, and etc.?
Yeah, so the CODIUM is mainly targeted for PV solar cells, but the DIATOM has a broader input range. So that means that it also can accommodate for other harvesters easily. Specifically, TG is very attractive. So TG has a lower output voltage typically, but the DIATOM has a larger boosting factor, so-called. So you can boost up the voltage easily to the level needed for the storage element. So that's really easy to integrate, PV and TG, also because they are DC. They provide a DC signal. Piezo can also be done. For piezo, since it's an AC signal, you first need to rectify it. So typically you have a bridge there to rectify the signal, and then you can feed it to the chip. For RF, that's a bit more tricky because it's all RF. So you need a matching network and a rectification. So it's doable. And the DIATOM definitely facilitates in it. It's always a question: is there enough energy around you? So you have to start with sufficient energy, otherwise yeah.
Okay, thank you so much. Okay, so another question is about how can we connect an antenna to your IC for RF energy harvesting? Do we need a rectifier between the antenna and your IC, or the rectifier is embedded in your IC?
The RF harvesting is specific for certain frequencies. So basically, you need a solution per frequency. So if you have a 900 megahertz signal that you want to harvest for, you need to have a rectifier indeed, and a matching network really dedicated to that 900 megahertz, for instance. And while you would like to harvest for a 2.4 gigahertz signal, right? You need a different matching network and rectification. So that makes it complicated to integrate it in the DIATOM and to make one uniform solution for it. So that's why this a matching network and the rectification needs to be external.
Okay, so you need an external rectifier. Okay, questions just continues to come along. So Another question is a question about if anyone has successfully applied energy harvesting in hazardous location environments where there typically is a concern about inductance and capacitance and arc, sparks, heat, and etc. So maybe do you have examples on hazardous conditions and energy harvesting in those conditions?
Yeah, there's several harsh conditions. One of the environments I'm thinking about is a farm, right? So you could have a tracking system for cows, for instance, right? And if you that's really a harsh environment. So it is certainly possible, right? But you have to really be careful with your electronics and to pack it really into the housing, right? And so that your really your electronics is not exposed. But I would say it's definitely feasible.
Yeah, and by using less components, you of course reduce the risk of the whole system.
Yeah.
So this would be also an advantage, and you can actually make it much smaller, accommodate it better. So this is an advantage, definitely.
Yeah, thank you. Okay, another question is about, would it be possible to have a TEG harvester on a smartwatch?
That for sure would be possible. It's about dimensioning, right? So what I was explaining, the energy budget should be there should be a certain balance, right, in terms of how much you harvest and how much you consume. If you would use it in a smartwatch, indeed, you could make use of the temperature body.
Yeah.
So then the other side would be the ambient temperatures. So if there's enough sufficient temperature delta, then for sure that would be possible. For TEG, you could already think of temperature deltas of like 10 degrees, then you would already have a decent harvesting. And then it comes up to the consumption side, right? So it also depends on the user profile of how you use your watch, right? So is it constantly tracking GPS, or is it right? Is it constantly on, or just during exercises or things, right? So there's also a big difference between like smartwatch or just a tracker, right? With all the so that equation needs to be made, right? And but TEG is really that could well be a solution.
Yeah, but it's possible to produce it, yeah. Okay, so there are a couple of questions about the radio energy harvestings, and I try to bring them together. I hope that works. So do you have any examples around the radio energy harvesting? And how reliable is radio as an energy harvesting solution? I believe this answers the questions.
Yeah, so to use RF as harvesting source is generally tricky in the sense that your energy transmitter needs to be really close to your receiving antenna, so your receiving harvester, because you lose a lot of energy over the air. So if the transmitter is like 5 meters away, then you lose already so much that very little ends up at the harvesting antenna. So then you start with really, with quite little energy. So it really depends on the application and how those things look like. But you could think of an application where you have a wireless keyboard in front of your laptop, for instance, and that the laptop could supply the energy for your wireless keyboard, so that you still have room to freely maneuver your keyboard. Same with the mouse close to a laptop.
Well, if you think about infrastructure, we have seen this a lot in towers for energy transmission and so on. As there are many of these posts, it's difficult to control the network. So what companies do, they put little sensors to know if the post is still straight up or starting to tilt. This is small data, uses little energy. So this sensor, this small sensor, it gives a very valuable information where in this vast area is something out of the right angle. And there we could maybe think about something like that. Or if you see the telecom towers, the antennas, themselves, right?
Mm.
This could be a nice application where you control if the infrastructure is okay.
Yeah.
And if there's any problem, that you can go to the right spot and do not need to check all the posts if all is okay. So this would be a possibility.
Yeah, yeah, for sure.
Okay.
And in analyzing the RF opportunity, what is important is frequency and its distance. So the lower the frequency of the transmitted signal, the easier it is to harvest, and the closer by, of course, it also gives you more energy. So those are things to assess when thinking about RF harvesting.
Okay, actually, there is this question regarding the RF harvesting. Maybe I can jump to that one. So, but do you provide RF harvesting solutions, or if there's any solutions available in the market now? So maybe can you
There
elaborate on
are
that?
some solutions in the market available, but it's questionable how much energy, how serious is it, right? Usually it's used next to another harvesting source. So then, yeah, is it a marketing issue, or is it really harvesting significant energy?
There's still a lot
yeah,
to do in the market.
There's still a lot to do. So, but yeah,
evolving.
but we see interest. We see people asking about it. But yeah, it is. It's difficult, or it's right. It's still to be seen. Comes with a lot of configuration and
okay.
But yeah, the theoretically it is possible, right? If there's enough energy arriving at the antenna, and then it's a matter of developing a good matching network, which is dedicated to that frequency, and then that would be possible. Yeah, for sure.
Okay, I can also tell you that there's an interest looking at these questions around the RF. Okay. Actually, let's complete the RF topic. Where there's another question regarding RF harvesting. How efficient is it compared? Sorry, regarding RF harvesting, how is the efficient comparing solar type of harvesting? I guess it's about comparing efficiency of RF harvesting to a solar type of harvesting. Is my understanding?
Yeah. So talk about the components in the chain. So for solar harvesting, a solar panel you directly connect to the PMIC. So basically, there's no additional loss in any way, right? So it's what's ending up at the input of the power management chip is that signal is being boosted, and depending on which chip it is, the efficiency can be up to 90% or even a bit higher. For RF harvesting, there's more components in the chain, right? So, and every component in the chain represents a loss. So it starts basically with the transmitting antenna. Then you have over-the-air loss. So how far is the receiving antenna and transmitting antenna apart? What is the sensitivity of your antenna? Then you get the matching network and the rectifier. So that's representing a loss. And then finally, it ends up at the PMIC. And the PMIC efficiency is basically the same as for a PV cell. That's not different. The signal might be a bit smaller. So that's a different, but eventually for the PMIC, it doesn't make a difference then once it's DC.
Okay. Thank you so much. And I believe now we can move on from the RF topic to another question. So what would be the maximum estimated power income if possible? So do you have a rough interval for power input? Yeah,
so the power input for our device, so we are basically targeting IoT solutions. So those are meant for low power consumption. So we are not on the roof of a house, for instance. It's just really small devices, and the target power application for DIATOM, it would be roughly 100 milliwatts that we can put through the PMIC. For the CODIUM, it's 2 milliwatts. So so that is enough to power things like a remote control, or nowadays you see those electronic shelf labels in supermarkets. that you can also make autonomous. They're also mainly asleep, and once every now and then they transmit. So those kind of applications are really suitable for the Nowi PMICs.
And then a lot of IoT sensors that are small,
Yeah.
that need little power,
Yeah.
that transmit few data, but of a higher value to the user.
Yeah, you could think of several things, right? All those devices typically they measure something and transmit it. So it could be like earthquake detector, or to track the cracks in the house, or those kind of things, right? So it measures every now and then transmits it, and it's asleep again. So those are, yeah, that's really the target market.
Okay, thank you. And another question is about what is the expected lifetime of the module with the capacitor?
That's a good question.
Yes.
I would say long, without quantifying it. It's just it's like with any electronics, there's no moving parts in there, right? Or no, so yeah, can last for tens of years, I would say.
Yeah. Also suitable
So
for IoT applications, for that matter as well.
Yeah. So eventually, I think it's the either the harvesting component or the storage element, right? Those are yeah. Some point they're end of life, right? So there's depending on the storage element, there's a number of charging cycles, right? And then kind of degrades at some point. So that would, I think, be the first that would degrade before the PMIC or yeah.
Okay, thank you very much. Going on with the questions in the last 8 minutes. So there is a quite specific question. So, is the energy harvesting technology with existing CODIUM or DIATOM right choice for an application which requires 5 volts, 40 milliamps in active volts, and 300 microamps during transmission? Is it a good solution? The specific use case? Maybe they need to contact you directly for this increase.
Yeah, this would be nice.
Yeah.
We have a form on our website where you can put in your data and the specific values, and then we can contact you and evaluate your case.
Yeah, maybe we can share this link in our email when we are sending the recording, and people can try out this form, if that makes sense, right?
Yeah, sure.
Thank you. Okay, moving on. Do you have any ready-made libraries in your solutions for developers to manage battery consumption and monitoring?
Yeah, what we typically do, we have an Excel file where we specify all the events that would take place in an application. So, for instance, you have a key press, right? A key press takes so much energy, and then you have a transmission that takes so much energy, and then we estimate how many key presses or how many transmissions a day there are, and then you add up with a calculation sheet. That's how we typically calculate the power consumption.
Yeah, there is a follow-up comment to that question. The frequency of switching on the device and the state of the battery charge must be included in the requirements. Ready-made libraries reduce implementation time. So yeah, it's just to support the previous arguments.
Not sure if I understand the question completely.
No, it is about the previous question regarding the ready-made libraries.
Maybe this would also be a question that we can answer after the webinar. So we would need to discuss this further.
Yeah, it's more. It boils down to a calculation tool, I guess.
Yeah.
And that's the question, I guess. Because a library, it's not really software or so, right? It's just a matter. Because and that is, it is important to understand your application, right? So that is key to energy harvesting. So the more you understand about your application in terms of power consumption, the better it is, right? So and of course the less you consume as an application, the less you have to harvest. So you can put a lot of effort in the harvesting system, but if you have a whole set of LEDs blinking constantly, right? So you have to consider, is this really needed, right? And can I live without, right? Or can I just let it flash every now and then just to save energy? So yeah, in that sense, you need to look at the whole application, both harvesting and consumption.
Yeah, thank you. And one of the final questions, does the Murata's ANDS solution work for indoor light harvesting as well?
It certainly does work for indoor light harvesting. Something to consider is that indoor you harvest less light than outdoor, given the same size PV cell. So a consideration could be to use a larger size PV cell to do this, and then it's yeah, we have to calculate how that works out. How much energy you can harvest indoor given a certain size, because typically there's certain size available, right? Your IoT application is not infinitely big, so that's the assessment that you need to make in that sense.
Yeah, but that is possible to use ANDS solution in indoor conditions.
Yeah.
Yes.
Thank you.
Yeah.
Now, this is not a question, but a participant shared a link to an energy harvesting watch. So maybe I share it also on the screen. So maybe afterwards we can have a look at it. I'm also curious. And last question is again to me. So the recordings of the last week's sessions will be shared this week and by the end of this week. Sorry for the delays, but they will be shared within this week. And with that, we are also through with the questions. So thank you very much, Ines and Gerrit, for this great presentation and the busy Q&A session of that webinar. And thank you for participating in the Learning Week.
Thank you.
Thank you. Bye-bye.
Thank you. Then I wish everyone a very great evening. And tomorrow at 9 o'clock Central European time, we will have an IoT security session with Keegan. So I hope to see everyone there. And until then, I wish everyone a good day.